Right now, you understand both how a class exists in C++, as well as how variables are created and stored. I want to take a minute and talk about the intersection of these two topics, where an instance of a variable, any variable, including objects like our cube class, can be stored three different ways. They can be stored directly in memory, accessed via a pointer, or accessed by a reference. Let's look into detail about each of these and how they interact with our class. As we learned, by default, all of the variables are directly stored in memory. When we have direct storage in memory, the type of the variable has absolutely no modifier. And the object size in memory is exactly the size it takes up to store. For example, we saw mini cubes. These cubes we talked about being stored in stack memory. We've talked about mini integers. And we've talked about crazy different classes like an HSI pixel. And we've talked about specialized classes like an HSL pixel you see in the assignments. You've also seen us storing things by pointer. We introduced the idea of a pointer when we started talking about heap and memory. And the type of a pointer is the type of the object modified with the asterisk. And a pointer takes on the memory value of another piece of data. And the exact length of that memory address is going to be the memory address width of the system. So for example, I'm on a 64-bit machine, and on a 64-bit machine, the memory address is 64-bit long. And as we learned with heap memory, a pointer simply points to the memory allocated for the object. And we see here's a cube pointer denoted by the star. Here's an integer pointer denoted by the star. Here's the HSI pixel, again denoted by the star. The star denotes these are each pointers. There's a third way of storing that we've made references to, but we haven't formally defined. That is storage by reference. A reference variable is a special type of variable which aliases existing memory by name and is denoted with an ampersand. So a reference variable never stores any memory itself. A reference variable has no size. It takes 0 bytes of memory to create a reference variable. A reference variable simply refers to some existing memory. And when you create a reference variable, we have to alias that reference variable at the moment we create it. For example, if we have a cube C that we're creating as a reference variable, it must be aliased to the cube, an existing variable, as soon as it's created. Int ampersand I is a reference variable I that's aliasing count. And again, it's taking on this alias as soon as it's being created. Because we're aliasing the memory address, when we change I or change count, we're changing the exact same thing. This is simply an alias to memory that's already created. It gives us a second way of referring to it. Because reference variables have to be assigned when they're initialized, we can see that the line of code HSI pixel reference variable p semicolon is not a valid line of code because that does not create an alias when it's initialized. And you'll see that if you run this code through a compiler, this code won't even compile. So let's look at why this matters in a real example. So suppose we're going to take our cube class and we're going to make our cube class currency. Our cubes have a value to them based on their volume. So a tiny little unit cube has only a volume of 1, and its value is just 1. So a little larger cube, a cube that has a side length of 5, has a value of this volume of the cube. So 5 cubed is 125, so a cube of length 5 is worth 125 currency. And likewise, a large cube of length 10 is worth 1,000 currency. So every time we create a cube, we're actually creating currency. So we're now playing the role of a banker. And whenever we receive money, we want to actually make sure that we get the cube itself. We don't want to create a copy of this cube. We don't want to do anything else except for transfer the cube to someone else. If we're creating a copy of a cube, we're creating inflation, we're being a bad banker. We want to make sure to understand exactly what's happening to this cube in memory. So what I've done is I've modified the cube class so that we have some output that gives us context on what the cube's doing. So here is 3 different functions of the cube class. The first function that I have here, lines 12 through 15, is a custom 1-parameter constructor. So notice the class name is cube, the same as the class itself. It has 1 parameter. We see it has no return value, so it has to be a constructor. This is a 1-parameter constructor, and it's going to say we created some amount of money. So whenever we call the constructor, we're creating money. The second type of constructor, the copy constructor we have here, takes in a cube by reference. So notice that this reference that we've thrown around before shows up, and this means we're not going to create a new cube when we pass this argument in. We're going to simply have the cube alias to us. And then this alias cube's going to copy into this newly constructed cube. So we see on line 19, we're going to say created, get the dollar amount via copy. So whenever we create new money via copy constructor, we'll see the via copy. So both of these constructors create new money. So we want to be very careful when new money is created. And the third function is the assignment operator. The assignment operator transforms an instance from one value to another value. So this again has the potential to create money. So we're going to say transformed, and we're going to talk about the current volume that the cube has beforehand and the volume it has after. So it's going to transform its old volume into the new volume. So it's actually changing the value of a cube. It's growing or shrinking the cube. So all 3 of these things are concerning because all 3 of these are creating money. So we want to be really, really careful about when these things get invoked in our code. And here we're talking about money, but in computer science, whenever an object is being created, it's taking up memory. There are resources really being allocated when all of these operations are performed. So we're seeing a real example with money, but this is actually a real concern in all programs because resources on a computer we want to be conservative about. So our very first example, we're going to look at what happens when we transfer a cube to another cube by value. So here on line 13, we create a cube of width 10. So we're creating a cube that's worth $1,000. And on line 16, we're assigning that cube to my cube. So because this is being initialized right here, and it's being initialized with an initial value, we expect for a copy constructor to be called. And here we're transferring the cube to another person. But what's actually happening at the end of this program is we don't just have one cube, we have 2 cubes because we constructed our first cube and then we used a copy constructor to create our second cube. So I expect that this program is going to create $2,000, which is not what we want to do. But let's go ahead and find out what happens when we run example 1 by value. Going into the CPP memory 2 directory, going into example 1, running make, running /by value. And by value, we created $1,000 and created another $1,000 via copy. Here we created $2,000, certainly something we didn't want to do when we just wanted to transfer $1,000 to another person. So we created some extra memory here. So let's see if maybe using a different memory technique will help us out. The second piece of code we're going to look at is looking at this by reference. So on line 13, we create a cube using the constructor. So we have a cube of $1,000. On line 16, we transfer the money to another person by aliasing the money because we have a reference variable here. So my cube becomes an alias of C. So what happens here is my cube is going to be this cube, as well as C is also going to be this cube. So because we're simply creating an alias of existing memory and not creating any new memory, we expect for the cube to be constructed exactly once and nothing else to happen when we run the by reference program. Let's see if that happens. I've already compiled this code, so I can just go ahead and run /by reference. And by reference creates a single cube worth $1,000. Awesome. So this gets to what we want. We only created a single cube. Now we have 2 different instances of this variable. Though in doing that, we haven't really transferred anything. We've just aliased 2 people to owning the same cube. So let's see other techniques and see what else we can do. So this third program in example 1 is going to create the same cube we've had before. So we're going to create a cube of $1,000. And then we're going to transfer this cube via a pointer. So my cube is going to be a new stack variable that is a pointer. So here we have a new variable called myCube. It's a pointer, and it points to the memory that C is defined in. So instead of having an alias where we have two variables that are directly the exact same cube, here we have two variables. One is the cube, and one is a pointer to the cube. So just like the by reference, we expect by pointer to only create one cube that is $1,000. Let's see if that holds true. Running /by pointer, we see that it creates exactly $1,000. Awesome. That's what we expect. Let's try to get something a little more complicated and something more akin to actually transferring money rather than just changing variables around. So up until now, we've just done everything inside the main function. But what we really care about is actually passing money around so that we can have a function like transfer money, that we can give money to somebody else. And similar to three different ways of storing access to variables, we have three different ways that we can pass variables around to functions. We can pass them by value, which is the default way. We can pass them by pointer by creating a pointer that we pass along, or pass by reference, which again is modifying by the ampersand and acts as an alias. It doesn't make a copy. It just makes two different variables alias the exact same memory. So looking at our first function, we're going to again look at by value, by reference, and by pointer. Looking at by value in example 2, we're going to create our cube again of $1,000. And now we're going to send the cube off to transfer the money to somebody else. And here we're sending the cube by value. So the cube is going into this function by value. And we expect, because it's being passed by value, that it needs to be copied from the main function to the send cube function. So we're going to expect here that it's going to send $1,000 or create $1,000 and then create another $1,000 via copy. So we expect to see $1,000 being created and then a second $1,000 being created via copy when we're in example 2 by value. Let's see what happens. Moving into example 2, running make to compile. And now running /by value. We see it creates $1,000 and then creates another $1,000 via copy. This copy happens when we call the send cube function, which sends the cube money somewhere else. Unfortunately, this way actually makes a copy, so you're really sending somebody a copy of your check and not the currency itself. Let's see if we can do better. Here we see a second example where we have a main function creates a cube worth $1,000. And this cube worth $1,000, we are sending using the exact same code as we used in the by value. The only difference we see here, send cube looks the same. When we look at the definition of send cube, it has an ampersand. We're sending this variable by reference. By sending this variable by reference, we aren't copying this variable anywhere. We're just sending an alias of this variable. Because no copies are made, we expect the cube to only ever have been constructed once and only $1,000 to ever be created. Let's find out what happens when we run by ref. Running /by ref, we see it creates only $1,000 exactly once. Awesome. Now let's look at by pointer. Finally, the very last piece of code is going to look a little different than the previous piece of code. We still create a cube worth $1,000 in memory. And now we send cube, and notice that we're sending ampersand of C. Remember, the ampersand operator before a variable gets the memory address of C. So we're sending the memory address of C into send cube. Because cube is a pointer, we need a memory address. So we're sending it the memory address to get to that cube, and C inside of this function actually points to this cube. So just like what you saw in main, we can manipulate memory as we're sending it through functions by value, by reference, or by pointer. And just for completion, let's go ahead and run this code And let's see that it only creates $1,000 exactly once. And then the pointer points to this object without actually creating a second version of it. Running /by pointer. Exactly what we expected. It creates $1,000 and it does that exactly once. The final thing to mention is that we can return by all of these different types. We can return by value, we can return by pointer, and we can return by reference. When we return by value, we're making a copy. When we return by pointer, we are going to return a memory address associated with that variable. And we return by reference, we are returning an alias to that variable. As we mentioned when we first talked about this, you should never return a reference to a variable that's created on the stack. It's just going to cause problems for you. The compiler hopefully is going to give you a warning, but you'll want to get out of the practice of ever returning by reference when you're returning an internal stack variable. We'll see more about this once we get into data structures. The big idea to take away is we have 3 different ways of storing variables. We can store them directly, we can store them by pointer, or we can alias to some other existing memory. So that is by value, by pointer, and by reference. These 3 different ways of storing data allows us to be really flexible and have a lot of control over exactly how our memory is getting copied around. This cube class provides a great framework for you to go play around with the code and really see how the cubes gets called when it transforms money, when it creates money via copy constructor, and all of the different things you can do with the cube class. So I hope you take a look at it, and we'll go back to talk about more properties of a class in the next video. I'll see you then.